Welcome to the first lecture of the third section of ESS 330. We'll spend the rest of the semester talking about models in ecosystem science and sustainability science. So, topics we're going to cover: what are models generally? What are the components of models? Why use models? The process of modeling, evaluating models, and the types of models. So what is a model? Well, a model in general is a physical or abstract representation of structure and function of real systems. So the word model is used very generally to refer to all sorts of different physical and mathematical structures. So for instance, in the upper left-hand corner, we have an example of a model that's a physical model. It's a scale model of a home. Beneath that, we have a conceptual model of the relationships between businesses and households and how they exchange dollars and goods. At the bottom left, we have a mathematical model that describes the relationship between an object A rotating around another object B. In the upper right-hand corner, we have a series of equations that describe the changes in temperature and volume of an air parcel in the atmosphere. Beneath that to the left, we've got a conceptual diagram for a climate model. So looking at the various flows or fluxes of energy and matter between cells in a grid that we use to model the evolution of the climate system. To the right, we've got a statistical model between doctors, number of doctors in the population versus female life expectancy. And then at the bottom right, we have a simulation model. So this is actually a flight simulation where, if you strip away the graphics, fundamentally, you have a model of how the plane is going to respond aerodynamically as a function of the given inputs of power and the position of the control surfaces. And right there in the bottom middle, there's a model in the sense that we'll be using it. This is actually a model of an ecosystem. It's kind of hard to see, but where you have photosynthetic inputs going to plants, herbivores, and carnivores, and then there being death in the form of either plant death or herbivore or carnivore death, and then decomposition. So that would be an ecosystem model. So all of these representations fall under the term model. So how are they similar? Well, they're all abstractions or simplifications of reality. They represent important features of more complex entities or processes and omit less important details. They're all useful for increasing our understanding of complex systems. They differ in the way that they're represented, whether you have boxes and arrows or interactive input into the simulation. They differ in scale, the number of dimensions, the complexity, the application, and the discipline. Some of them are statistical or empirical. Some are mechanistic, like the model of the interactions between two objects at below left. Some are theoretical. Some are based on laws of fluid dynamics and physics. Others on theory or observed human and animal behavior. So models you've already seen in this class, well, we've been doing statistical models so far. That is an accepted use of the word model to talk about relationships you've developed and to call that a statistical model. So length and mass of fish at the upper left, exponential population growth on the upper right, and then a statistical model picked using an AIC factor. People say that models are a map of reality, but what is a map? A map is a symbolic depiction to achieve abstraction. So it highlights important objects and relationships. And maps for different purposes feature different sets of objects and relationships. So really a map is a subtype of model rather than a model sort of being equivalent to a map. And here's a comparison of sort of a real life set of observations you might make out on a, on the left on a grassland. These are wildebeest. And what do we see? Well, we see wildebeest of different size. We might be able to tell males from females. And we can see that they are getting their sustenance from the forage in those areas. And on the right, here is this abstracted model that you could make to try to link the herbivores with the availability of forage. So abstracting out of observations similar to the ones made in that photo on the left, you might come up with relationships over a time series of forage density. So the plant cover, snow depth, whether or not which would control whether or not they could actually get to the foliage, and might also tell you something about how well the foliage is going to grow later in the year. And that would give you some idea of the available energy in the form of nutrients that the wildebeest could eat. And then if we're interested in the state of the population of wildebeest over time, then fundamentally we're interested in the size and number and sex of individuals. So you can see in a particular model of wildebeest, we start toward the bottom left with some rate of calves being born, and then we're modeling. You'll see that little square box that indicates a state variable, the number of calves that are available at any one time. Calves, you can see the arrows leave the box containing the number of calves at a particular time to mortality, or they are advanced into immature females or immature males, both of which also have mortality. And then the immature females and males advance to mature females and males, again, with some mortality component. And all of these feed back on the available energy from the grassland itself. So that's one way to look at this reality, but we've said models are abstractions. So what we're going to use to represent reality becomes a key question. So at the left, we might have, the bottom left, we might have an agent-based, individual-based model. That is, we might have a model where all the rules are written in terms of individual animals, and then their access to resources, their growth rate, and their potential for mortality. Alternatively, in the middle, we might represent that area as a population model, as we did in the previous figure that I went over. You know, what are we interested in there? Well, we're interested in the number of individuals of a particular size, of a particular sex over time. And so we might just model, as we did in the example I discussed, just the number of individuals of that particular size / sex class. And then on the right, we might model as an ecosystem model in which we're not interested in individuals at all. I've got sort of a blurred out photo of a wildebeest and a blurred out photo of some grass, and I've got them sort of sitting on a scale. And in this case, we might only be interested in the mass, the biomass of wildebeest and grass, and model the rate of, say, uptake of the grass resources as a function of the total mass of the wildebeest. So 3 different ways of looking at the same system. And so really it's a question of how we want to conceive of our system that makes any one of them right or wrong. So what is an ecosystem model? So physical or abstract representation of structure and function of real systems. Okay, it's going to be an abstraction of reality, or our understanding of reality. An ecosystem model is very generally a set of equations or computer code that defines interactions and quantity flows that drive changes in state variables or stocks. Models started as systems of equations that were solved analytically, and then moved to discrete mathematics. So a branch of mathematics where it was not necessarily capable of analytical solution, but you could model time varying processes without the analytical solution. And it moved to being increasingly computer code driven, which allowed for even more flexible representation of processes. So ecosystem models are often represented conceptually as box and arrow diagrams. So the boxes in this case are the pools or state variables that represent the number or amount of some object of interest for us. So pool A could be number of juvenile wildebeest, and pool B could be mature wildebeest. Pool A could be grassland biomass, and pool B could be wildebeest biomass. It all depends on how you've defined your models. And then we have these arrows, and each one of them represents a flux, which is a movement of material into or out of one of the pools. So a pool, synonyms would be a reservoir or a stock or a state variable. So that's a quantity, and it is what we're keeping track of in the model. Flux is a flow or a rate of input or output. So it's a quantity per unit time. And that's how material is moving from one pool to another pool, or as you can see in the cases of flux 1, flux 2, and flux 4, we have fluxes that go to or from a pool but aren't defined on one end. So like flux 1 is just a flux into pool A, and we haven't decided, or we haven't specified where it comes from. Flux 1 could be something like sunlight that is coming in at we might model at a constant rate. Well, all we need to show is that something's coming in. We don't necessarily have to show you the details of where it's coming from. Similarly, flux 2 and flux 4, we have a material or individuals moving out of pools, but we're not specifying where it's going, and depending on our purposes, we might not ever have to specify where it's going. So your goal is to build models in such a way that the pools and fluxes are measurable, so you can test how well your models work. And we can translate this diagram to a set of mathematical equations. So we have pool A and pool B. We have flux 1 might just be x sub t. So that might be a time series of, like I said, it could be a time series of solar radiation. It could be a time series of the rate at which juveniles are being added to a population. All depends on your definition. The other fluxes here are specified as rates times the quantities in the pools from which they come. So we have flux 2 has a associated coefficient K2, and we're going to say that the total flux out of pool A is going to be equal to K2 times whatever is in pool A sub t, at the time that we're evaluating these equations, and so on and so forth. And we can go down to the bottom, and we can say for any given time period what the we can update pool A and pool B as a function of their prior time period and whatever fluxes happened during that time period, and get an updated pool A and pool B at time +1. And you could put this in a simple loop and do calculations just that way, just updating these values over time. Now, in practice, it gets a little more complicated than that because of the fact that in general you want to do your modeling at a time step that allows all the components of the system to be updated continuously. So you don't want to use just a time period of, if all your processes are measured in, per second, you may want to have a calculation that is done at a sub-second temporal scale, but this gives you the general idea. What do we need for models? Well, very often we need inputs, or we sometimes refer to them as forcings. So that could be a weather input, temperature, precipitation, solar radiation, and humidity. Could be CO2 concentration in the atmosphere. And it could be a time series of disturbances. So the presence of fire or harvest or storms. We need state variables. So those are the things that we're going to monitor, and we're going to look at the change over the course of the simulation. We're going to need to specify initial conditions for them, and this could include things like plant biomass, soil carbon, soil moisture, population. We're going to need a set of parameters. Okay, the parameters themselves are generally constant during the course of a simulation, but they may change between locations. So if you want to use the model in a new place, the parameters may change. And these, refer to things like decay rates or growth rates or carrying capacity that ultimately control the change in your state variables. And then you may have rules of change. So these will determine how the state variables change over time in relation to the current values of the state variables, forcings, and parameters. So here's a model, and you know, you look at it at first glance, it might look complicated. You know, we tend to use a very common visual language when drawing models. So rectangles, less frequently rectangles with rounded corners, represent state variables. So here we have a model that's keeping track of above ground and below ground carbon in living materials. We have the standing dead, carbon and standing dead materials, surface structural C and metabolic C, below ground structural C and metabolic C. You don't have to understand what all these things are exactly at this point, but microbial C, etc. So those squares, those rectangles are going to be your state variables, and then we have these little sort of cloudy little things, and those generally represent sinks or sources for the model as a whole. So these are things that, for instance, in the upper left-hand corner, we might keep track of the amount of above ground live carbon that's being harvested per time step, and then we might have this little container where we keep all the harvest removed in terms of sort of total carbon over time. And so that would allow us to keep track of that. On the upper hand right, we have the sort of the opposite, which is net primary productivity. So that is a pool from which you know, carbon is introduced into the system. And then at the bottom, you can see there's another sink for this system where materials are leached out of the soil compound into, you know, the water table and then forth perhaps the streams. So those materials are, again, after they have been removed from the system, no longer monitored. And of course, we have our arrows, and those show you the fluxes from one state variable to another, and those all have these little double triangles on them. Almost all of them do. And those double triangles indicate that there's a rate associated with those fluxes, and probably an equation that allows you to calculate how much is being moved per unit time as a function of other state variables. And then finally, there's a bunch of arrows here that don't have those little triangles on them, and those are all fluxes of CO2 to either the atmosphere or to, you know, the atmosphere within soil pore spaces. So it's not that complicated when you break it down and understand how to look at it at levels. What are the state variables? What are the sinks and sources? And what are the fluxes? So here's a statistical model that we worked with to look at fitting the equation that we use there. You know, number of time t is equal to the number of times 0 times e to the power of some coefficient r times t, and that gives us a population growth. But if we want to look at this as a model, we probably want to break this down into the sum of processes. And so here we have a model of population over time, where we have, starting at the top line there, we have that little, again, kind of cloud symbol. That is the symbol that's used in the program we'll be using for our modeling, Stella. So that's a source, okay? And it's basically saying any number of things can come from this source. but it's going to be controlled by that little valve. That's supposed to be a valve. It's a pipe and it's got a valve, and the degree to which that valve is opened is going to be a function of both the population at any given time, okay, and some intrinsic birth rate that we're going to give it. Then we have our state variable, population. This then, we're going to have a flux of population away from that state variable, so that's death, okay? And those deaths are going to be the magnitude of that flux is going to be proportional to the population, but then it's also going to be a function of a death rate, which you can see there's a little red arrow coming up from the food available, okay? So deaths are going to be proportional both to the number of individuals in the population and a death rate coefficient that is itself a function of the food available. So then if we look at that bottom line there, what do we have? We have, starting from the right, okay, because the arrows are pointing the other way, starting from the right, we have some source of food for this population that's going into the food available state variable, and that is just at a constant rate. There's no dependency on anything else so far. And then there's going to be, based on the food available, consumption flux to the left, okay, out to some sink that, again, we just no longer deal with it. And the rate at which food is going to be consumed is going to be a function of population from the top line, the food consumed per member, which is going to be some constant. I'm sorry, that's a function of the available food, and then that food consumed per member is going to go up into the consumption flow in the diagram out to the sink. So you've got two coupled state variables, one population, one food available, each with its own dynamics. And the models are defined by these kinds of dynamics. The most general, kinds of dynamics are either positive feedbacks or negative feedbacks. So here we have a very simple conceptual sketch of how much water is in the ocean. This is the upper left, okay? And then we have some flux of evaporation to water in the atmosphere. Well, the more water you have in the atmosphere, the greater, you can see with that red arrow, the greater the greenhouse effect that you have. Note that in Stella, the program that these are being created in, red arrows are information arrows. So it's not that water is going to the greenhouse effect, it's that the water in the atmosphere state variable is being used to calculate some greenhouse effect with the water, which is going to increase the temperature of the atmosphere, which is then going to increase evaporation. So this model, whether or not it's purely applicable to the actual world, works this way. You have water in the ocean, you have evaporation. The more evaporation there is, the more water there's going to be in the atmosphere, the greater the greenhouse effect, the greater the temperature of the atmosphere, and the greater the evaporation. And so if we think about going through this in multiple steps, we're going to get an increased amount of water in the atmosphere over time that is itself going to increase the evaporation. And so that's a positive feedback. Evaporation leading to more evaporation. Now on the right, here's an example where you have water in the oceans and you have evaporation, which leads to water in the atmosphere. But the water in the atmosphere increases the cloud cover. And the more cloud cover you have, the higher the Earth's albedo. And so you have more energy being reflected off the Earth, because albedo, I'm sorry, is just the fraction of the Earth's, the incoming solar insolation, solar illumination that's being reflected back up into space. And so that's going to decrease the amount of evaporation. So you have water in the oceans, there's evaporation, there's more water in the atmosphere, but that leads to more cloud cover, a higher albedo, and then a lower rate of evaporation. That's a negative feedback. Evaporation leads along this particular set of mechanisms to less evaporation. Why use models in ecosystem science? They aid in understanding and communicating ecological principles. So when developing models, we explicitly formulate and organize our ideas. And so it's like writing a well-organized research paper. You're having to define what you think is important in a particular system, and how the things that you think are important are related to each other. Models are a simplified representation of more complex phenomena and processes, and so it helps us determine the level of detail necessary to understand the processes we're studying. Models can simulate processes that are difficult or impossible to measure in time and space. Models are used to perform experiments we could never do in real systems. Models can be used to guide research projects, including data collection and hypothesis testing, and that goes back to model-guided fieldwork as a way to strengthen the value of fieldwork exercises. And then models can be used to predict outcomes or dynamic changes. So how will changes affect systems in the future? How are systems going to respond to management or disturbance? So for instance, how will increased atmospheric CO2 alter community composition in the shortgrass steppe over time? The effects of increasing CO2 are many, and they interact. And so really the only way that to get a comprehensive view, a comprehensive answer to that question is going to be using a modeling framework. Another reason to use models is sensitivity analysis. So you can do this by changing parameter values or the forcings into a model and evaluating how sensitive the model results are to those changes. So here we have soil carbon losses versus soil texture and tillage practices for a number of different scenarios, and this allows us to determine what important factors are and which factors are important and which are not under what circumstances. Okay, the main steps of modeling. Conceptualization. You need to define the model's purpose, its boundary and states, as well as the flows between them and the key parameters and variables influencing the flows. States, of course, are going to be defined in terms of quantities that you're going to keep track of, and where you have a finite amount of material that has to be accounted for. Your boundary, your model boundary, separates out where the states have to remain in balance and the sinks and the sources that you may not have to account for. So like sunlight coming in, you don't necessarily have to account for how that energy is getting to the system. On the other hand, CO2 being respired, you don't have to, that may go outside the boundary of the model to something where you're not actually keeping track of it. You need model formulations. You need to convert those concepts into code, or a graphical representation of code, and that's what we'll be doing. And you need to estimate your parameter values. Calibration, in general, you're wanting to adjust your parameters and input variables so that the results that you're getting, both the pools and the fluxes, match observed values from the real world. And then validation, testing your calibrated model against the new set of observed values that were not used for calibration. And this is, in general, an iterative process. That is, you don't necessarily expect you're going to go from conceptualization to validation and then write a paper or provide a result for someone. Instead, your expectation is that the process of doing this may make you rethink some of your prior decisions, and you may have to go back and do this multiple times to get a reasonable calibration and validation. So here is an example where you're looking at a model to track pollutants in ground and surface water. You need to define the flows of both water and contaminants into the system. You need to define the mixing rates of the two of those, and you need to define all of the other potential physical reservoirs where water can be exchanged with the stream. So, and I'm using reservoirs there in the same sense that I would use, say, state variable or pool. That is, you'll have some exchange with shallow groundwater, deep groundwater, etc. And so you're going to have to come up with rates for the exchange of water between those various pools or state variables in order to make this model work. So the last slide was model conceptualization and formulation, and now here's an example of a calibration. So this is from the 2007 Physical Science Basis chapter developed by the IPCC, and here we have a mean precipitation observed at top and simulated below from 1980 to 1999. So that gives you a calibration of the fact that your model is doing well. How are models evaluated during calibration and validation? Well, accuracy, the ability of the model to correctly predict the data. A model is considered inappropriate when it can't fit and explain the data. Generality, the number of scenarios, processes, or ecosystems in which the model is applicable. And realism, the degree to which the mathematical model relates to the ecological concepts for which it was intended. So you can think of those as a series of hypotheses, where each part of the mathematical model is a hypothesis about how the system is working, and those hypotheses may or may not fit what we actually know about the natural world. And so determining realism may require expert judgment or novel data sets that allow you to determine that realism factor. One way to get better confidence in your model predictions is to look at more general trends from a suite of predictions, so a suite of models. And so the IPCC does this with climate change projections, and there is a long-standing project that is the Model Intercomparison Project, Climate Model Intercomparison Project, CMIP. So on the left you have the CIMP models from time 3, And on the right, you have the models from time 5, and you're comparing various scenarios with those two sets of models. And so the different colors are for the different scenarios, and the variability due to which model you're looking at is the shaded area around each line. So you can see you can actually get a very good idea of just how, in my opinion, little variability there is as a function of the actual individual model versus the variability due to the different scenarios for greenhouse gases. One thing to keep in mind is that a good model is not only one that's capable of reproducing the observed changes in a natural system, but it also should produce insight into the dynamics of a system. So we might have a model that can generate the observed pattern that we're interested in, but has no underlying basis in fact. So just a purely descriptive model. And in that case, it's not a good model because it tells us nothing about the underlying processes that interact in that system. So a good dynamic model will, by its nature, be predictive. And this is somewhat in conflict with the development of artificial intelligence models, which may do a good job of predicting dynamics, but don't have, at least currently, any necessary links to physical processes that would make sense. So, types of models. We'll talk about statistical as well as theoretical or process-based models, deterministic versus stochastic models, static versus dynamic models, and phenomenological versus process-based or mechanistic models. We'll talk about what those mean in the next few slides, but just note that models can have combinations of these characteristics. They're not mutually dependent. Statistical empirical models, so these are predicted values depending on some observed value and some constants. They're usually not the kind of model we're interested in systems modeling. However, systems and simulation models may include statistical empirical models as components. So for instance, you might have a model that models fish populations in terms of a series of length classes. Okay, so you're going to keep track of the number of individuals with a particular range of lengths. But you might also need to know at some point their individual or total mass, and then you could use a relationship like the one at the bottom of the page to generate those masses on an empirical basis. Now, if you have individuals that are fall outside of the range of lengths that were used to create your relationship, then that is going to lead to you extrapolating the relationship, and that may lead to problems. Theoretical models, these are based on laws in nature. We talked about this in terms of the confidence one would have in a model of the orbit of one planet around another. Obviously, we know the mathematical relationships very well, so we'd have a lot of confidence in that kind of model. These usually have terms with some kind of scientific, in this case biological, significance. So here's an example for photosynthesis where we've got A is representing assimilation, so uptake of carbon. AN is the net assimilation, and that's going to be calculated as the difference between that big ratio there, which is the total assimilation, minus daily respiration. So this is on a daily basis. And that big term there is saying that the total assimilation is going to be equal to the product of the maximum possible assimilation, Amax, which is something that can be measured directly, at least at the leaf level, times fractional par. So the fraction of the photosynthetically active radiation, that's par, that that a leaf is exposed to, divided by, again, Amax plus that fractional par. So that has it's a relationship with some biological significance that you can see if you adjust the light levels for a particular leaf. Deterministic versus stochastic models. So deterministic model does not attempt to include the effects of random variability in forcing functions and parameters. The inputs are just values, and the same input into the model is going to give you the same output every time. A stochastic model attempts to include the effects of random variability in forcing functions and parameters. So you might have an input of sunlight. If it was deterministic, maybe you just have some value for the time of day. Maybe you'd be interested in the effect of cloudiness on say photosynthesis. Well, then you might include some sort of mean and variability of that par in the sunlight over the course of the day in order to see what the effective variability is. So the variability is both in forcing functions, like we were talking about with sunlight, and also in parameters. So you have a value for a particular parameter, but very often, like say for instance with Amax we were just talking about, you might have a distribution of values of Amax that you've measured for a particular species. Well, you could just use the mean, or you could also run the model several times using multiple iterations with different values of that parameter and see how the output changed. This is also a way you can incorporate random events like weather, hail, frost, lightning strikes. See if their presence and absence and timing actually make a difference on the output of your model. Phenomenological models versus process-based models. So phenomenological models are things you can measure, but that may not be the actual thing that you're interested in. So for instance, you can include elevation or day of the year as a variable in a model. However, a more process-based method might use air temperature, which is much more highly related to the physical processes going on within organisms than is elevation. You might include, instead of day of the year, you might include soil moisture or day length as your variable. So we tend toward wanting to use things that are more mechanistically related to a variable or a process than ones that are more abstract, like elevation or day of year. Now, on the other hand, if you were measuring or estimating barometric pressure, then elevation might be the variable that you're interested in. So one thing to keep in mind is proceed with caution. Models are one of many tools you can use to analyze a particular physical system. They are approximations of what's actually going on. You shouldn't necessarily take the output of the models as being more applicable than your validation of them suggests they should be. Even good models can be used inappropriately, because people take models and use them without fully understanding their limitations. There's a balance between model complexity and general utility. That is, the more complex a model is, the more difficult it becomes to understand why it's doing a particular thing. For complex models, individual components of the model should be tested independently. So if you've got a soil moisture subcomponent to your model, then testing that against soil moisture data sets independent of the overall evaluation of the model makes sense. Uncertainty should be evaluated. So that's the idea behind the IPCC model suite comparison approach, in that rather than taking the output of any one particular model as verbatim truth, the mean tendency of the model is the thing that's being considered, and then the variability that the models generate given their somewhat different bases. And so you should always be skeptical of model predictions. And again, this is why the IPCC has gone to multiple models, because it does improve your confidence in what the output means for the future. And there's this famous line by George Box: all models are wrong, some are useful. So all models are imperfect, but that doesn't necessarily mean that they can't be used for your purpose.